Hey everyone, this is a preview of what we're going to be seeing tomorrow on day 4, and this can be viscosity and Reynolds number. And this is our first encounter with a real type of fluid. Yesterday we saw, rather today we saw ideal fluids, and so when you describe a real fluid, you need to account for viscosity. And there's a couple of different quantities that we call viscosity. One is the kinematic viscosity, which is what's normally called dynamic viscosity, called eta divided by rho divided by the density. So kinematic is eta divided by rho, but usually we're going to be talking about just viscosity, and that means the dynamic viscosity, which is called eta. This is the Greek letter eta. The unit of the viscosity is the Pascal second. Also, we used PHYS or centiPHYS, and a PHYS is basically 10 to the minus 1 Pascal second, and a centiPHYS is 10 to the minus 3 Pascal second. The crucial equation to take into account for these types of fluids is called sometimes the Hagen-Poiseuille equation, or just the Poiseuille equation, or Poiseuille's equation. And what this equation tells you is how much pressure difference you need across a pipe of this type of some length L and cross-sectional area A to send the fluid through it with some viscosity eta if you want the average speed to be V average. And so if you have all those parameters, then the pressure difference that you need between one of the endpoints and the other endpoint of the pipe is 8 pi times that average speed times the length times eta divided by A. So if A grows, then you need less pressure. If L grows, you need more pressure. And if eta grows, you need more pressure, and so on. Of course, with the speed, with the velocity, if you want the fluid to move faster, then you need more pressure. You can turn this equation around and write the V average in terms of the pressure difference, the cross-sectional area, and the other parameters. And so that gives you this equation. And so it tells you what type of pressure difference and cross-sectional area and so on you need to maintain an average speed V. So here we talk about the V average because the velocity profile of a real fluid in a tube, in a pipe, looks like this. We'll talk more about this tomorrow. The important point is that there's going to be some average speed because the speed depends on the position, whether you're closer to the walls of the tube or not. So we'll talk about that tomorrow. And once you have the average speed, you can multiply by the cross-sectional area and calculate the flow, what we call today the flux or volumetric flux. So V times A then becomes this formula for the volumetric flow in a real fluid with some viscosity eta. And notice how it's proportional to A squared, and areas are usually proportional to radii squared, and so this whole thing will be proportional to the radius of the pipe to the 4th power. Okay, so that will become important. So another quantity that's important is Reynolds number. We'll talk about that as well. Reynolds number is basically a ratio of inertial forces to viscous forces, and we'll see an example of a viscous force given by the drag force on a sphere that's trying to move through a fluid with some speed V. It's given by this formula. That's the drag force. We'll talk about that, and we'll talk about inertial forces as well. And when you put all these things together, and you can do a quick assessment of the units, dimensional analysis. When you do all that, you get an estimate for a Reynolds number that is rho divided by eta, so density divided by viscosity, times the diameter or length scale of the object you're studying, times the speed of the flow. So we'll make sense of all these quantities tomorrow. So that will be the content of tomorrow's lecture.